Today we're going to continue our discussion of stoichiometry, this time adding in another conversion factor, one we've used many times before, and that's the one for molar mass. So these problems today are ones that we will very possibly have to use a molar mass conversion factor in order to solve. So take this first example. We're going to tack it the same way. How many moles of carbon dioxide, so we want moles of carbon dioxide is what we're looking for, can be produced from the reaction of 250 grams of oxygen. So that's what we're going to label on our balanced equation. It says we have 250 grams of oxygen and that we're trying to find X moles again. So that's our unknown of carbon dioxide. Sorry, I almost labeled the wrong one. So X moles of carbon dioxide. Remember, X out the ones that we're not dealing with on this particular problem. And we're going to underline these coefficients so that we can make a mole ratio out of them. So let's do that over to the side. We know that according to this, we have 5 moles of oxygen for every 4 moles of CO2 and 4 moles of CO2 for every 5 moles of oxygen. And now do yourself a favor and mark those coefficients out so you don't try to use them again in the problem. Now remember, we've always started our problem with whatever we've got underlined. So we're going to start with the 250.0 grams of oxygen. Make sure you're labeling it the same way that it is in the problem. Remember that oxygen is O2 because that's going to be important, because look at what our first term is. It's grams, not moles. So we're not going to be able to start with our mole ratio. Our goal is always going to be get to moles as soon as you can so that you can use the mole ratio and switch to another substance. Because we don't want to know about oxygen. We want to know about carbon dioxide. So let's do the only conversion factor we've got that involves grams, and that's molar mass. And we know that there are 32.00 grams of oxygen per mole. Remember, oxygen is 16.00, but there are 2 of them, so it's 32.00. This is going to cancel our grams. And now that we've got moles of oxygen, we are going to be able to use our mole ratio. So it looks like we need moles of oxygen on bottom in order for our moles of oxygen to cancel or reduce to 1. So it looks like we're going to need our second conversion factor that has the 5 moles of oxygen on bottom and the 4 moles of CO2 on top. Now, once you've used the mole ratio, start checking, because you want to make sure that you have your answer in the correct units. And since we're trying to get to moles of CO2, that's exactly what we have here. So it's time to stop the problem. Don't keep going. And we're going to solve this by taking 250 divided by 32 times 4 divided by 5. And when we do, we get 6.25 even. Looks like we need 4 conversion factors, 4 sig figs for our answer, because the 4 and 5 over here do not count. They are infinite sig figs. They're exact numbers. So 4 sig figs means we're going to need to add a 0 onto the end of this. Now you could put times 10 to the 0 since we don't need to move the decimal, but you may prefer to just leave it like this. I do not care. I usually just leave it like this. And that's the answer to our first problem. Okay, let's look at the next one. We're going to do it exactly the same way. We're going to attack it by finding what we're looking for, what we're trying to find, how many grams of oxygen. So this time we're looking for grams of oxygen, and we're given 10 moles of water. Okay, this particular one doesn't start out with a balanced equation, so we've got to write it in. So you've got to have a balanced equation. So 2 C2H2s plus 5 O2s yields 4 CO2s plus 2H2O. So if you do not have a balanced chemical equation, you must write it in. So once I have that, I'm going to start labeling everything. I know I have 10 moles of water, so 10.0 moles of water over here, and I'm looking for grams of oxygen. So X grams this time. This is the first time we've had our X be a gram value for these stoichiometry problems. We're going to X out the ones that we don't need and underline our coefficients so we know what to use for our mole ratio. I'm going to fit it in up here, the fact that there are 5 moles of oxygen for every 2 moles of water. Now, the one thing I am going to do on these problems is to let you write only one conversion factor. You do not have to flip it. We've done that enough. So just write one of the conversion factors. You know that you have to flip it if you need to. So coming back down here, then, we're going to start with what we have underlined, which is the 10.0 moles of water. Now remember, our goal is to get to moles as soon as you can, so you can use the mole ratio where we're already in moles. So we can go immediately to the mole ratio. In this mole ratio, we're going to need to have moles of water on the bottom. Make sure you write the full unit. Guys, you cannot figure out how to use the mole ratio. Just putting moles isn't enough because you have to have the substance in order to be able to determine how you need to flip that mole ratio. Looks like the way it's given is correct because I need the moles of water on bottom. So 2 moles of H2O on bottom, 5 moles of O2 on top. So that's going to cancel my moles of H2O, and I've got moles of oxygen. Let's see if that matches what I've got circled. Not yet. I need grams of oxygen. So what are we going to have to use next? We're going to need our molar mass conversion factor, table grams per mole. We need moles of oxygen on the bottom. And unless we're dealing with the mole ratio, anytime we have a conversion factor, what number always goes with mole? 1. All of our conversion factors are based on 1 mole of a substance. So 1 mole of oxygen on, 1 mole of oxygen on bottom, 32.00 grams of oxygen on top. So that's going to cancel moles of oxygen. I'm left with grams of oxygen, which does indeed match our unknown, what we circled up above. And when I take 10 times 5 divided by 2 times 32, I get an even 800. Well, it looks like from the data that I have 3 sig figs here and 4 sig figs here. The 5 and 2 don't count, and of course 1s never count. They're exact numbers, infinite sig figs. So it looks like I'm going to need 3, the least number, 3 sig figs for this. I need to get this in scientific notation, so I'm going to need to move the decimal to here. And since it's a large number, it's going to be a positive. And since I need 3 sig figs, I'm going to keep those zeros because now they're significant since they're following that decimal. So 8.00 times 10 to the positive second, and I wrote it over a little bit too far because I'm running out of room for my units. I'm going to rewrite that because I have had several students write their units wrong whenever they see that. So 8.00 times 10 to the second grams of O2 for our answer. Okay, our final example, if you can do this one, you can do any of them because this final example is as hard as it gets for our mass conversion stoichiometry problems. So let's attack it again. We're looking for grams of acetylene gas, and it's giving us 75 grams of carbon dioxide. This is not showing a balanced chemical equation. Your paper may, but if it does not, then you need to write it in. So we're going to write in again that we have the 2 C2H2s, acetylene, plus the 5 oxygens, yielding 4 CO2s, plus 2 waters. And now we're going to label our information. We're looking for X grams of acetylene gas, and we're given 75.0 grams of carbon dioxide. X out the substances that are not involved and underline those coefficients. Notice nothing is in green. All of this has to be there. The one concession I am making is that you only have to have one of the conversion factor pairs. So this says that I have 2 moles. Do not just put 2 C2H2s or I will count it wrong. 2 moles of C2H2 for every 4 moles of CO2. So that's the conversion factor I'm going to be able to use. I'm going to start with what I have underlined in the problem, which is the 75.0 grams of CO2. Our rule, remember, get 2 moles as soon as possible. So I need my molar mass conversion factor. I need grams of CO2 on the bottom. And if I add up 1 carbon and 2 oxygens, I get 44.01 grams of CO2 for every 1 mole of CO2. Remember, the 1 goes with moles. That cancels grams. And now that I'm at moles of CO2, I can use my conversion factor, my mole ratio. I need moles of CO2 on bottom. So in the one that I chose to put up in brackets above, looks like that's going to work with the 4 moles of CO2 on bottom, the 2 moles of C2H2 on top. That's going to cancel my moles, and I have moles of C2H2. Be careful because you'll try to stop not realizing that that does not match what I have up here. I need grams. So I need a final conversion factor of grams. Looks like in this case, moles of C2H2 go on bottom. What always goes with mole? 1. The only time that changes is in our mole ratio. And I need to look up our molar mass for C2H2. And if you add up 2 carbons and 2 hydrogens, you get 26.04 grams of C2H2. That's going to cancel moles of C2H2. I'm left with grams, which is what I want. And if I take 75 divided by 44.01 times 2 divided by 4 times 26.04, remember always multiply by what's on top, divide by what's on bottom, I get 22.188 for my value. Sig fig wise, looks like I've got 3 sig figs here, 4 sig figs here, and 4 sig figs here. So I'm going to need 3 sig figs. Let's get it in the correct scientific notation first. I've got to move that decimal 1 place. 22 is a number greater than 1, so it's going to be a positive exponent. And so I've got 2.2188, sorry, times 10 to the, and I moved it 1 place, moved the decimal just 1 place, so times 10 to the first. Now draw your sig fig line. I said I needed 3 sig figs, so I'm going to draw the sig fig line here. So rounding that to the correct number of sig figs, I end up with 2, let's get that in the right color, 2.22 times 10 to the first grams of C2H2. Notice that the things that are in green or black don't have to be on your paper. Those are just interim values and working with it to get it in scientific notation and sig figs. But everything that's in red or blue must be on your paper to get full credit. So that's the answer to our mass stoichiometry problem.